All right, I guess we'll go on to the program. We have Daniel Gall, right?
Yep.
And he works with Ben. He's currently serves as Chief System Engineer for L3 Harris JWST Imaging Weather Satellite Team. They're in Fort Wayne. Daniel received the National Outstanding Public Leadership Medal in 2020 for extraordinary commitment and leadership in the development, integration, test, and post-delivery support of the GOES-R Advanced Baseline Imagers, and obtained his PhD master's degree in physics from Purdue, and a bachelor's degree he got in engineering physics from Taylor University.
Thank you.
So with anything, I'm gonna flip this back around.
Oh, all right.
And you have to be on TV.
Wonderful.
Good thing I'm shy.
Yeah. All right, let's see.
Twisted so his head's done cut off.
Yeah, yeah.
You got it.
There you go. That should do it, hopefully.
So this should be good.
All right, so hopefully, can everyone out there online see the screen? I think I'm sharing.
Yeah.
Or did I lose it? Oh, I am.
there.
Okay, all right, great. Okay. Thank you very much for the introduction. I'll just say just a real quick, a little bit about my history, what I've done, or getting, academic history, I guess, because I've kind of transitioned from, I've known Ben for a while back from academia, and now we're both in industry. So this is kind of my path. I have my BS engineering physics from just down the road here at Taylor, and then did grad school at Purdue. In the middle of all that, I've worked at the same company, but it's been 4 different names. So you can see ITT here. I did an internship, did a postdoc out at the University of Iowa, and this is a picture from some of that work there. And then been since 2013 at Excellus, and then Harris and L3 Harris, again, all at the same site up here on Cook Road, which many of you are familiar with. So, and this is my family in the middle who keeps me sane. My oldest daughter, Cora, is here in the front row with me tonight. So. So what did I do in my graduate work? So like Ben, I'm sure he's given you some good background, but I built a lot of skills in data analysis, image processing, statistics there. I worked on Veritas, which is this gamma ray observatory shown here out in southern Arizona. I've discovered, well, I kind of knew, but I really learned when I was there at Purdue that I really liked hardware, building things, making things work. So I tried to kind of pursue that as I went through my academic career, both working at Veritas, and then when I did my postdoc at University of Iowa, which is where Cora was born. Continued working on Veritas, and then I also worked on a space mission, which was an X-ray telescope, helping work on calibration for that mission that unfortunately ultimately got canceled, but that led to me coming back here to Fort Wayne. I didn't say it, I grew up here in Leo, Indiana, so just up the road. So we got to come back to Fort Wayne, working at L3 Harris, and still working with NASA Goddard on space technology, but a little bit different. So I was working on telescopes pointing up before. Now I'm looking at telescopes pointing down. There's a lot of commonality there. So everything translates really well. I was looking at gamma ray, X-ray, and optical astronomy, so multi-wavelength observations. Now I'm doing the same thing, looking down, but down in visible and infrared. So still multi-wavelength observations, a lot of the same physics that plays over. When we're looking at the Earth, we care about certain spectral regions of interest, both where exciting things are happening. So windows where we can see features in the atmosphere, or water vapor bands where we see the water vapor in the atmosphere. And then, of course, we need to look at wavelengths where we have detectors that work really well. So when we're looking at Earth observation, I'll tonight mostly be talking about visible through infrared. There's also observations that happen with microwave and radar as well. Again, I am going to eventually get to some astronomy topics here, but I'm starting with our weather satellites, which is what we use for this astronomical study of Betelgeuse. So I promise you I'll get there. It's going to take me a little bit, but bear with me. So just again, trying to talk through the difference or the commonality between astronomy and what we do with weather satellites. So there's a lot of the same fundamental physics principles bound the performance of our instruments. So, our diffraction or PSF of the system is driven by the telescope aperture, and you can see some cartoon pictures of what that looks like here. We do a lot of work making sure our images are clear, crisp, and have good quality. So we look at what's called the optical modulation transfer function, or MTF. That's the optical performance of the telescope and other optics. And you can see an example up here, looking at different sort of performance in that MTF performance, how well it's working. We care about how well our detectors are working. We want to make sure we have detectors of the right size to sample the images we're looking for. We want to make sure they're sensitive in the wavelengths we're interested in. We want to make sure they have good noise performance so we don't have a bunch of blurry images. We also have to care a lot with satellite remote sensing about stability. So we have to make sure the satellite's stable, that our optics are stable, we don't have jitter affecting the image. And then, you know, a lot of the same physics that you have to worry about when you're worrying about astronomy. So why do we use satellites for weather? This is kind of a fundamental question. You know, you might have weather station in your backyard. That's going to tell you very locally what's happening in your backyard. We have a radar station up near Lake Wawasee that covers the northern Indiana region. That's telling you what's nearby. Satellites can see the whole Earth, and depending on the orbit, it sees different parts of the Earth. So this is a very busy cartoon here, but you have like polar orbiting satellites that'll get the whole Earth over time, over a day or two. You have geostationary satellites that are staring at the same spot all the time. Basically, for predicting weather out long term, you need to know what's happening everywhere to know what's going to happen in the future in your backyard. So again, we use multiple orbits for our weather satellites. So we talk about two primary orbits when we're talking weather: low Earth orbit, or LEO, which is essentially a polar orbit. And there's some cartoons here that show this. So low Earth orbit, we call it low because it's only about 500 miles, about 500 miles out above the Earth. You're orbiting very quickly. This is like where the space station is. And so you're going about 17,000 miles an hour. You get about 14 orbits a day. You're going around about every 1.7 hours. This gives you global coverage. So you're going around the Earth as the Earth is spinning beneath you. So you get global coverage over the course of a day, multiple times. And then we talk about geostationary orbit, which is much higher. You're 22,000 miles away, more than 22,000 miles away. You're orbiting above the equator, so that essentially you do an orbit of the Earth every time the Earth rotates in a day. So you're parked above the same spot all the time, rotating around. You get a consistent, persistent view of the Earth. You're seeing about a third of the Earth, but you see it all the time. And this is more important for short-term forecasting. So like when you see the hurricane tracks on the news, that's from these geostationary satellites that are staring and looking all the time. So again, I'm working at L3 Harris just up the road here, and we are specialists, I would say, in the visible and especially the infrared range. There's special technology you need to make sure you have long-term quality observations. So our weather instruments, again, they're 22,000 miles away in space. You're not sending a person up there to fix them or service them if anything's wrong. And they have to last long-term. Our missions are 15 years on orbit. So 5 years of storage and 10 years of operations on orbit. And these are operational satellites. They have to be working all the time because you don't want your satellite to go out in the middle of hurricane season, then you'd be blind to what's coming ashore. So we have to work to build very reliable solutions, but they also have to be very precise. So our temperature measurements, so essentially with our infrared measurements, we're measuring temperature. Again, 22,000 miles away, we have to measure temperatures in the atmosphere or on the ground within a degree and consistently do that for 15 years. So we have to have very precise calibration, traceable to standards, so that, you know, just because we're looking with one satellite, if someone looks with another satellite, they should get the same answer. So we need to be cross-calibrated and have really good knowledge of our truth of our measurements. So again, the range we're specializing in, you know, when I was doing grad work, I was way out here in gamma rays and X-rays, but now our specialization here for the weather is primarily, at least what I'm going to be focusing on tonight, is in the visible out to infrared. So why do we look there? We're looking at two things. So we are seeing with the weather satellites visible and infrared light. So sunlight is kind of around here. This is just a very rough cartoon diagram. So the visible's right there, the peak around green. And we're also seeing infrared. So sunlight, when we're looking at visible, we're looking at reflected light from the sun, basically. In the infrared, you're looking at light that the Earth is emitting because of the heat of the Earth, because of what's in the atmosphere. So you're looking at, you know, reflected sunlight versus actually light emitted by the Earth. So we call it reflected versus emissive light. And what do we see? So if these images are taken to the images of the Earth, again, reflective, you're looking at sunlight reflecting off clouds. You know, we do have some channels that are really particularly pick up vegetation. So you're looking at crops. You're also looking at different features in the atmosphere besides just clouds. Emissive, again, this is light just because something's warm. So, you can see it by eye if you have red hot steel, but you'll get, as things get cooler, you'll get dimmer and dimmer and get to longer and longer wavelengths out in the infrared, which is why we look for things like water vapor and cloud temperatures with the infrared wavelengths. And so as far as what we're talking about wavelength wise, when we're talking reflective or visible light, we're talking less than 3 microns. Emissive, we're talking longer than 3 microns, so midwave and long wave infrared. So just a little bit of a background. What, again, L3 Harris up the road here used to be ITT for many, many years, a couple other things in between. What does that group look like? There's about 600 employees there. About 75% have STEM education, 31% with advanced degrees. So it's a really interesting group I get to work with, some of whom are here tonight, or who I used to work with. We've been there more than 60 years building these very sensitive weather payloads. I'll talk a little bit more about the history in the upcoming charts. And our main focus here in Fort Wayne is weather. We're also looking at some other applications of those weather sensors too, which are very interesting. But again, we look at solving really difficult problems with our technology. It's really interesting work, really fun work. I've enjoyed my time there. And we, again, are delivering the most advanced sensors in this band. More than 75 payloads over those 60 years, and we've never had basically a mission-ending failure driven by any of our technologies. So you can see some of our customers here. So the weather for the U.S., NOAA is the operator of the satellites. Our customer is NASA. They work with NOAA to procure the satellites because they're experts in space and space technology. They're operated by NOAA, who provides our forecasts. We also work with international customers for our weather products. So, and that's what I'm going to focus on tonight when I actually get to the astronomy part. We do have versions of these satellites that the U.S. uses for Japan and South Korea. So we have those customers there. And we've also, again, like I mentioned, leveraged some of that weather technology for missile warning and missile defense, which has some other U.S. government customers, which are very interesting too. And there's a picture of our building, again, corner of Cook and Lima, just up the road here. So here's a little bit of our history. Again, I talked about those more than 75 payloads over 60 years, going back to the 60s with the very first Nimbus 1, the very first weather satellite, all the way out to the GOES series, which I'll be talking about mostly now, GOES R, S, T, and U, as well as our international variants, which are Himawari 9 and GeoComSat 2A for South Korea. So a lot of history here. And we're very proud of the quality and the service we provide. Again, these are operational satellites. They're predicting forecasts, predicting hurricanes, saving people's lives. And an interesting note here, I have this note about some of these instruments are going to display at the Smithsonian. The previous generation was the GOES N, O, P, and Q. They're lettered in the series. They never launched Q, so I think they ended up decommissioning it, and it's sitting at the Air and Space Museum now on display, or it will be on display soon if it's not yet. I know they're doing some renovations. So this is an interesting one. I like to bring this slide up. This is, I mentioned Nimbus 1, the very first kind of space-based meteorological satellite. You can see the list of contractors down here. IT&T Labs produced the high-resolution IR radiometer. Here, it's actually, this is from a magazine article back there in the 60s. You can see the contract value for that radiometer, $139,000. So, to give you context, the next gen geoimager that we just got a contract for is $765 million. So things have gotten a bit more, they're a lot more advanced too, but there's, prices have gone up since then. Yeah. So yeah, so here's the next generation that I just mentioned. So again, I'll talk a little bit about the generation that's up there flying now, but I just wanted to mention this too. We just this year have gotten a number of new awards to, again, I mentioned these missions are long-term, right? So 15 years on orbit, the ones that are up there launching now, we started developing those around 2004. The first one launched in 2016, and the last one will launch this coming April in that series. And so those last for about 15 years. It's a long development cycle. So we're working now on the next generation, what's going to replace those. And this is an image. I mean, we're really proud of what we build. Again, I keep saying this over and over again, but again, we have the East and West satellite over the US. We have our Japanese and Korean customers here. And we also have one of the previous generation versions of the GOES imagers is actually over the Middle East. So we basically have a ring of these instruments built here, right here in Fort Wayne, that are covering the entire globe from geostationary, which is pretty exciting. And this is the next generation constellation we're working on now. Again, it's visible infrared imager on the east and west. This is our Japanese customer. They're actually going to fly 2 kinds of instruments on the next gen Japanese satellite. I've talked a lot about imagers. You're going to see lots of pictures of imagers tonight. That's pretty easy to understand. You're taking 2D pictures of the Earth with basically a camera. Sounders are a little different. They use interferometry and they basically can measure a 3D picture of the atmosphere. So you're getting, 2 dimensions plus depth. So you can actually measure moisture and temperature to get a 3D picture of the atmosphere. And that helps still feed these numerical models that need good initial conditions to propagate out a 3D picture of the atmosphere. So the images are focused on, again, hurricane tracks, tornado outbreaks in the Midwest, short-term forecasts. The sounders are feeding numerical models that go out further in time, modeling that atmosphere. So I just wanted to show a few pictures of a little bit of what this looks like for the build and test of these instruments. And Ben, if you can pass that model around, this is a scale model of the instrument we'll be talking tonight, which is what we call the Advanced Baseline Imager, or ABI class imager. So this is a scale 3D printed model. The real thing is a little less than 6 foot cubed. So it's quite big, and you'll see the scale of that, some of these pictures coming out. And you can see the real size version here. This is in our lab in Fort Wayne doing some optical testing. This is in our thermal vacuum chamber, which it's really unfortunate there's not a person in this picture. You can't really get the picture of the scale, but these are this thermal vac chamber that pump down the vacuum and bring down to the temperature, cold temperature of the space is about, I don't know, 3 stories tall. Who's been out there? I'm trying to look at it's big, right? So these are made to fit, you can fit like a school bus up at it in these. They're very large. And this is our EMI lab where we're testing for electromagnetic interference. So we have, we're measuring emissions from the instrument. There's other instruments on the spacecraft. There's the spacecraft itself. We don't want to mess with radio signals. We don't want to mess with observations. And we also want to make sure if they blast us with some RF energy, we're not destroyed by it too or damaged by it. So we do that testing as well. This is all done at the instrument level. When we're happy that the instrument's good, we send it out to the spacecraft provider. And there you can get a little bit more sense of the scale. So again, the model that was passing around is this instrument right here, kind of at the top here. And there's some people sitting here for scale. So this is where we're getting integrated into the spacecraft, which again, when you have the instrument plus the spacecraft, it's about the size of a school bus before they fold out the wings. Here's a picture with the spacecraft, the solar wing unfolded during a test, and you can see some people in this. And here's the thermal vac chamber out of the spacecraft provider, again with people in there for scale. So you get a sense of the scale of these things. So again, they have to last a long time on orbit. No one's going up to fix them. So they do a lot of very, very rigorous testing to make sure they're working.
Do you have redundancy like that?
Absolutely, yeah. Everything, we basically are required to not have single point failures. If there are certain things that are, you can't have like multiple bearings on a motor. Right. But pretty much everything, redundant electronics all the way.
Not the cameras though.
Even the focal planes have redundancy, full redundancy. Yeah. So, yeah.
I have a question. What happens after the useful life, 15 years or so?
Sure.
Is expired? What happens to these satellites?
So they'll keep them running as long as they can. Basically, what bounds the lifetime is the fuel on the spacecraft, because once you get to geostationary orbit, you're constantly tweaking yourself to make sure you stay, because you have perturbations from the moon and other things that are always trying to push that spacecraft out of an ideal perfect orbit. You also, if you look at this picture here, you'll notice the spacecraft only has a solar array on one side, because the other side we need to be able to have a clear field of view to reject all our heat to space. So imagine you're sitting out there, the sun's pushing on that solar array too, it's trying to move you because it's uneven and unbalanced. So you're always using up some fuel and thrusters in the spacecraft. And that's when you run out of fuel, you're not going to be able to correct for those perturbations anymore, and you'll start drifting out of your orbit. And essentially when they get close enough where they know they're running out of fuel, they'll boost it up to a higher orbit, because you don't want something drifting around in geo where you have a bunch of communication satellites and other things that you don't want to damage. So you just boost it to a higher orbit. Again, you're 22,000 miles out. You're not going to deorbit it because it takes way too much fuel. They just push it to a higher orbit and it'll stay there for the next couple 100,000 years and hopefully be out of everyone's way. So stuff down in Leo where you're 500 miles up, there are now requirements that you have to save enough fuel at the end of life to deorbit. So you're not up there drifting and crash into something and then create a bunch of debris. But in geo, you're just so high up, you're never gonna, your orbits don't degrade. You're far enough out of the atmosphere. You're not degrading like you do in Leo. So it'll basically stay there virtually forever. I do have, oh yeah, so if everything looks good, you pass through all these tests, then you actually get to go and launch. So this is taking the spacecraft out. The testing for this one was done in Denver, Colorado. They have to get to Cape Canaveral to launch. So the way they do that, they basically get a C5 Galaxy and just drive a big truck on with a trailer full of the satellite, just right on that plane and fly it out and then unload it. And this is some of the pictures of integrating it to the launch vehicle and the team out there at the launch, and then the launch itself. And I think I actually have a video here. Yeah. So just a quick summary of, I got to show a launch video, right? Yeah.
Ready. That's automatic.
Ready.
Communications.
Ready.
Those are.
Ready. Launch ready. LD's ready. The dynamic machine will not be transported to that. Roger.
Yeah, you know.
It kind of leans with it. There's real time.
Status check to proceed with terminal analysis of propulsion. Go. Hydraulic. Go. Pneumatic. Go. LO2. Go. Anomaly chief. HQ. Go. Range coordinator. Clear to proceed. Launch director. Launch director is go, and you have the mission office. Status check. Go. Go. Centaur. Go on. 5, 4, 3, 2, 1. And liftoff of NOAA's GOES are America's most advanced weather eye in the sky, elevating environmental intelligence to new heights and saving lives. Good. Finding zero painful attack phase appointment. Fire control program is complete. Fire exit controlling down the Mach 1. And we have first pair and second pair. Good preparation. And we have failed ranges.
Oh, so that didn't have it, but there's always at the end of the launch, there's this last little video when it gets to its geostationary transfer orbit and you just see the satellite floating off, never to be seen again, which is very exciting. Anyway, so that, yeah, I've been lucky enough. I've gotten to go to all 3 of these launches. Cora's been to 2 of them. So, so once they get up there, what does that imagery actually look like? So again, the current generation looks at 16 bands or colors for atmospheric characterization. This is kind of a mosaic of looking at all of them here. Here's some of the properties of all those 16 bands. The wavelengths, what kind of SNR measurements we see, and what sort of features they're typically used for. So you can see very clearly that, you know, some of these are more in the visible range up here. So you're seeing clouds, you're seeing ground features if you zoom in on these. Some of them don't look like anything you'd imagine looking at Earth. This looks more like Venus, right? So these are the water vapor bands. They're just looking at the water vapor circulating around the atmosphere, which are used for a lot of these higher level weather forecasting products. And this one's always very interesting. This is a 1.38 band, and that's very, very dark. It's those bright white features, and that's the cirrus cloud band. So it's picking out those really high, thin cirrus clouds, which are very hard to distinguish from snow unless you have a measurement in this wavelength where they're very bright. And here's what it actually looks like if you look at the visible. This is a 3-color image in the visible, looking at what RGB kind of imagery would look like. And this is a week in 2020 when there was a record number of storms. So you can see all these hurricanes spinning up off the coast of Africa and slowly making their way across towards the US and the Gulf. So this is a particularly active week. A couple things to point out in this image, which is interesting. You'll notice this flickering every once in a while up here. You'll see that's nighttime. So what's happening there is, where's that model? Yeah. So if you're imagining you're sitting up here looking at the Earth all the time, you're rotating with the Earth as day goes and you see the light. The sun, you can just think of the sun going around you. So we have the times of the day when the sun, nighttime on Earth, the sun's right in front of us, looking right in the aperture. So we don't want to stare at the sun with our sensitive detectors. So we actually will automatically know when the sun's there and stop scanning. So there's chunks there, it looks like bites out of the earth almost, because we just don't scan near the sun. It looks like these bites taken out of the imagery to avoid the sun. So this is what the full disk image looks like. I'm going to assume this is a 4K projector. If I wanted to show this in true resolution, I'd need like 60 of these projectors to do a mosaic to get this in full resolution. So if I take one of these storms and zoom in to the actual resolution, what it looks like, here's the actual imagery resolution. So yeah, we're getting about 1 terabyte of data down a day from these satellites. There's just a lot of imagery there. So this is just a nice view. You can see these cloud systems within the eye. And you can see with this resolution, we can really precisely track the motion of the storm. And we actually will have, this is a time when a hurricane was coming ashore here. You can see the coastlines coming into view. They'll actually sometimes, if there's people in need, they'll watch this eye and say, okay, first responders go out, you have 30 minutes while this eye is going over to go help people, and then get back in now because here comes the eye wall where the severe weather's coming. So we also use it, again, we're looking at a lot of bands. One of them is thermal band that's really good at detecting fires. So this is an example. This was a Marshall fire in near Boulder, Colorado in 2021. You can see in the visible imagery, this plume of smoke here from the cloud. But if you look up here, this is some of our thermal channels. You can see that fire shows up really, really clearly in thermal. And again, we will detect things as small as like, this is typically they'll use this to chase wildfires and watch their propagation, but we'll see things as small as a very small, like structure fire. Again, 22,000 miles away in space, we'll see that within maybe a couple minutes of it actually igniting. And so there's pilot programs, especially out in the West, where the forecast offices will watch this fire channel and actually call in fires, and often they'll call in before they get calls from the ground because of the sensitivity there, especially in these remote areas. Okay, so now I just get to send these cool examples of what we can do with it. So this was, if you remember that Tonga volcano, the huge volcano out in the South Pacific, this is looking at, some of our bands are looking at water vapor in the atmosphere, and these look a little funny because they're difference images. They're just taking, we get an image of the full disk or the full Earth every 10 minutes, and it's taking one image and subtracting it from the image 10 minutes before just to look for small changes. And when that volcano went off, and you can see the imagery, the visible and infrared of the volcano. When it goes off here, you can see the shock wave propagate all the way around the Earth. This is the goes west, and you can see it come on into view when it's reset. You can see it come into view and it goes east and go all the way around to the exact opposite side of the Earth over Africa. And you actually see it bounce back a couple times. So it's pretty impressive how sensitive these things are. I mean, to be able to detect that shock wave that goes around. So again, just some other notable imaging systems. I'm talking all about weather imagery and weather satellites tonight, but there's some probably very familiar telescopes that we also have a hand in. So the Hubble Space Telescope. What's interesting there is, I think probably this group is very familiar with the story of Hubble when it first got launched up there. There was some issues with the mirror and had to have corrective optics flown up. There was actually a backup mirror made for the Hubble that never flew that L3 Harris made. It did not have the issue with the polishing. It was correct, and it's sitting, I think, out in a museum somewhere now. So,
be a big sign. This one works.
yeah, right. So the other one that's so there were a series of great observatories. Hubble was one. One people don't hear about quite as much as the Chandra X-ray Observatory, which is looking, again, very much like Hubble, but it's looking at X-rays. We did the mirror assembly and alignment of that system, and that's shown here. That was a very impressive system because it's using, because it's looking at X-rays, it can't have just like a normal reflector where the light bounces straight in, bounces off like the Hubble. It does this thing called grazing incidence mirrors. And so you basically have X-rays coming in at a very slight angle of the mirror and just slowly getting focused over time. And you can imagine those mirrors have to be very precise because you are coming in at such a steep angle. You worry about deformations or aberrations in that mirror. And they have to be aligned very precisely. And the I think in that case someone left a lamp on next to the fixture for aligning it, and they were seeing enough thermal distortions from that lamp giving off some heat and warming up the mirrors that they had to revisit their process to get that aligned well. Again, that's up there and still operating just like Hubble is today. James Webb Space Telescope, we did mirror alignment work there as well, and some of the integration. And then the Nancy Grace Roman Space Telescope, which is going to be like a wide field of view survey telescope that actually is using a surplus mirror that was built for another mission that is being repurposed for astronomy. So that's pretty cool. Also at our Rochester facility, we built a lot of Earth imaging satellites over the years, many of which are feeding the Google Maps images that you have on your phone or on your computer when you're looking. So why am I talking about weather satellites here? I got there eventually. So why am I talking about these at the Fort Wayne Astronomical Society? So star observations in astronomy are actually a really big part of how our instruments work. So I mentioned earlier, you're sitting up there on a satellite that's in geostationary orbit. If everything's perfect, if nothing's drifting, you're perfectly pointing at the Earth all the time. Nothing's ever moving, but nothing's perfect, right? So you have that spacecraft. It's going to be moving up and down. It's going to be tilting back and forth. It's going to be moving around all the time. You also are going to have thermal loads that change over time, right? Like I said, the sun's going around behind you where it's not on any of your optics. It's going to be in front of you where you have all this huge thermal load from the sun right on your optics. So your line of sight, not only from your base moving, but also your optics distorting, is moving all the time. So how do we adjust for that? We actually are looking at stars all the time with our weather instruments. We actually point the mirrors. The field of view is big enough that we can get this kind of annulus around the Earth of space. And we use that for two reasons. One, we use it for a dark look for calibration. And the other thing is we will actually look at stars. We have a special set of star catalog for looking at with our weather instruments, and we're pointing at those all the time. We use those basically to inform a model of the line of sight that will track and predict where we're pointing at a given time to both kind of navigate where our main channel, the visible channel, is pointing, but also register. We have, again, 16 different bands. They're all kind of in different places on the instrument. They have to all be registered to each other too. So if you measure, this place with the blue channel, you want to make sure you're measuring the exact same place with the red channel if you're going to compare those images for weather products. So like I said, we have a dedicated star catalog that's on board the ABI. It's used to point at these stars in the annulus around the Earth. They have to be far enough away from the Earth. The Earth is very, very bright. So you don't want to be washed out by the Earth, but you need to be close enough that we don't have a huge field of view. We don't want to have to be able to have our instrument designed to look way over here to look at stars. We want to be able to just be very optimized in our scanning. So from geostationary, the Earth's diameter is about plus or minus 8.7 degrees. So our star catalog is basically designed. We go out and select stars that can be viewed by the channels or the colors that ABI can look in, and also to be within about plus or minus 10 declination. So it's within our field of view around the Earth. So we take those star measurements. We also there's very precise instruments on the spacecraft that measure how it's moving, called gyroscopes. We get data from that. We also get data from the GPS satellites. Again, we're way up in geo, so we're actually above the GPS satellites. The GPS satellites are more in medium Earth orbit. I think they're around 8,000 to 10,000 miles up. You probably know better than I do, but they're below us in the orbit.
Yeah, they're not geos. There's 32 in the constellation.
Yeah. So we're actually, on Earth, you're below those GPS satellites. We're above them, so we're actually getting signals from GPS satellites on the other side of the Earth from us. The lobe of their radio signals coming around the Earth. So we use the GPS data for our orbit position and how fast we're moving, and then we use those gyros to tell us what our angles are, and we correct for all that and propagate, and we use the stars as truth to update that model and propagate over time. So this is kind of what that looks like. There's a few things plotted here. Essentially, what we're looking at is when we look at stars, we get a truth value of where we're pointing, and we can always compare that to our model of where we think we're pointing. And you obviously want a very small value there, right? You want to have your truth update or your updates to that model to be very small. That means your model is moving along fine, tracking where your line of sight is very well. This is comparing the current generation, GO16, with the previous generation, GO13, how those residuals compare. And you can see these are on the same scale, these plots. So you can see we're, maybe plus or minus 50 over here, and over here we're well within plus or minus 5 probably. So you can see some areas highlighted here where we do have some larger residuals of our local midnight. Any idea why those might be harder times to track? Local midnight for Earth, Ben knows. Anyone else have a guess? I kind of mentioned it already. Local midnight, again, that's the time when we cut out those pieces of the observation to the sun's there. So the sun's the sun's going right down the barrel of the telescope. So that's going to distort your optics and move things around a lot more. But even then, we're tracking it really well. So it's still less than 10.
So are those units
microradians.
Oh.
Yeah.
So I don't know.
Let's see, there's like an arc second is like 4 microradians-ish, I think. I have to check my math.
I don't know, I'm just multiplying by 57,
Yeah.
which is about 60, so you said 5 micro plus or minus 5?
Yeah, yeah.
5 plus 6 is plus or minus about 30 micro degree, 300 micro degrees, which is small.
Oh, sounds right. Yeah, that sounds right.
I don't know.
Your scale,
Yeah.
you held up a nickel a mile away. One microradian is about what a nickel subtends, if it's a mile away from you.
There you go. That's a good example. Yeah.
So what improvements were made from one generation to the next?
So a lot of improvements. There's a number of improvements, both on the spacecraft side and on our side. The previous generation was the navigation system there was based on how good the pointing actually was, making sure you're pointing in the right spot at the right time. The current generation with GO-16 with looking at these star observations, it's based on knowledge. So as long as you know where you're pointing within reason, you're going to be able to navigate out and take out any pointing errors you had. With the previous generation, you had to be really good at making sure you knew what the spacecraft was doing, so you were adjusting for it with the mirrors in real time, where you're going to have some pointing errors. So going to knowledge base versus, actual pointing precision is what drove a lot of those improvements. So, and you can see this is an example of that kind of the knowledge base taking out some of one of the things we did during post-launch testing is you have just a very regular diurnal trend where, when the sun's coming in during the hot time of the day, you do see very big changes, but you see kind of a slow drift over time through the day. So this is an example of that. The blue dots here are showing star residuals kind of before some tuning that we did. And then we actually subtracted out and adjusted in real time for those regular diurnal, diurnal motions. And the black is what you see after that. So there's some of this, slowly varying stuff we can take out, just in our actual pointing, and then again, use the knowledge to get it down from, this is like, what is this, maxing out at maybe 20 or 30 down to the 5, looking at 5 or less we saw before. So there's a lot of other stuff we do during post-launch testing. We'll do one-time adjustments to our detector maps to take out plate scale and tip and tilt and things like that. So this is another comparison. This is kind of maybe more easy to visualize. This is looking at, this is just kind of an overall view of how it looks with the new generation. This is a side-by-side of the same image for the previous generation and the current generation. Now this comparison is a little bit unfair because this was during a solar storm when we have a lot of issues that can happen with the spacecraft. And there were some issues with the star tracker for this spacecraft as well. So its pointing already was not that good. But you can see just the amount of stability. I mean, this is pretty rock solid when you look compared to these coastlines here for the current generation. So this was a huge improvement over the past generation, even though this is kind of a worst case example. I like to show it. So what do the moons and what do things look like? What do celestial objects look like with our, I'm getting closer to the astronomy part, I promise. So we look at stars for navigation all the time, but also I will say for fun, we can look for other things. And it's also important for other reasons too. So we do have lots of incidental observations of these celestial bodies. So you can see in this top picture here, let me use the pointer so everyone can see. If you look very closely, you can see a crescent moon here. And then over here on the side is Mercury. And if you kind of saturate this and really blow up the gain a little bit or the contrast, you can actually see features on the moon, and you can see Mercury. The Earth gets very saturated though. So we actually regularly see the moon all the time and many of the planets all the time. And that's actually important for the other reason I mentioned what we use these space looks for is calibration. So we look at space periodically to give us basically a zero signal, a very dark signal for our detectors. You don't want to have Jupiter sitting in what you think is zero signal because it's going to throw off your calibration quite a bit. So we actually track the position of the planets and make sure we are skipping space looks or moving around space looks or rejecting space looks that happen to have planets in them. And this is from a colleague of mine that works for NOAA, who actually was an astrophysicist before he does what he does now too. He actually went and dug up this imagery, and this isn't used for anything operational, but you can go look at the image. So this is Mercury. This is actually Venus when it's kind of in a crescent phase, Mars and Jupiter. And then these are, this is stacked, this image is stacked to get a better picture, obviously. And this is kind of an animation over time of what all those look like. And they're bouncing around a little bit because his script is just basically centering on a brightest pixel, which isn't always the best way. But anyway, so we want to make sure we track those so we don't contaminate our calibration looks. Again, we see Mercury, Venus, Jupiter, Mars regularly. Anyone have a guess on why I don't have a nice pretty picture of Saturn in here? Remember, I said the field of view is plus or minus 10 declination roughly around the Earth. Anyone have an idea where Saturn is right now? So Saturn's declination, unfortunately, has been way outside our field of view. But the good news is, I think around 2024, beginning of 2024, it's going to drift in. So I'm really hoping we get some really nice pictures of Saturn with some rings here to add to this chart. So that'll be pretty cool. Oh, okay. This is one more look. So we talked about the planets a lot. If you look, probably hard to see in this projector, but if you squint real close, you might notice this isn't a perfect arc here of the limb of the Earth. So you might think there's a little bulge there, and you'd be right. It's the moon trying to come out from behind the Earth. And if you look close at this image, you can see this curves quite a bit. And if I turn the contrast way up, you'd actually see this curve goes out and goes around. And you can actually see the entire moon in this image because the refraction of the atmosphere will actually bend the light from the moon about a half a degree, up to half a degree by the time it comes out on our side. So, you know, the moon's about a half a degree in our field of view. So we're seeing a lot of stuff bending out from around the back of the Earth because of that atmospheric refraction. And we have to worry about this for that. Again, we don't want the sun. We don't want to be looking at the sun. So we have to worry about this for our solar intrusion. We can't just think about geometrically, when's the sun out from behind the Earth? We have to think about that refraction and add a little bit to that exclusion region. So yeah, oh yeah, I forgot I had this in here, zooming in a little bit on that moon image, and then there's what the nice moon looks like after coming out from behind the Earth. So, all right, I finally got to it with not much time left. So the great dimming of Betelgeuse, this was, I thought, a really good topic for this group because it's not just talking about cool pictures, it's talking about some actual science that was done with this, you know, these incidental observations of stars that happen. Betelgeuse is actually one of the stars in our star catalog that we use for navigation, but these scientists had no idea about that. But what happened was in, I think around late 2019, right before COVID hit, there was this sudden dimming of Betelgeuse that wasn't expected. No one knew the cause. By more than a factor of 2 of its brightness. It's a semi-regular variable, so it has a periodic cycle, but this dimming was not part of that regular cycle. And so some people thought, well, it's on the verge of exploding. Maybe, you know, we know this one's a star that's getting close to the end of its life, but it wasn't really expected soon. But by the end of February 2020, the fading stopped, and within the weeks, the star was back to its regular brightness. So there's a lot of interest in this. And this is kind of a picture of some of these observations of the dimming during this time. So there's a nice paper on this, a Nature paper. I brought some copies. If anyone wants to pull this for actual, you know, more details, I'm just going to give you a very high level summary. But if you want to take the paper and read it, you can take a look. I brought some copies, but it's from this paper from Nature Astronomy. So there were several observatories after this was observed, this dimming was observed, started focusing observations there. There's a team that used the Hubble to observe Betelgeuse, and they got lucky. They had one observation before, then it started dimming, so they got observations during and then one after. And they concluded there's like a big blob of hot material from the surface created this cloud of dust and started obscuring the star. There was another team in China that saw a drop in temperature of Betelgeuse, about 170 Kelvin. So they said, well, it's not dust. The star just cooled off for some reason. That's what dimmed it. And then there was another team that used this, the VLT, this image here on the bottom, it's pretty cool. They said, well, it's something like a little bit of both. So there was a drop in temperature, but there's also some dust cooling. But because this wasn't expected and it suddenly happened, and Betelgeuse is a really pretty well-known star, there's not people out there looking at it every day. There weren't long-term light curves at multiple wavelengths to monitor this over time and see, you know, what it was doing before, during, and after in detail. You can't just have like 1 or 2 observations. You really need a continuous curve over a long time to distinguish between these different models. And a team of Japanese grad students actually realized, hey, we have this weather imager and it's looking at these pictures of Earth, and there's Betelgeuse. It's within plus or minus 10. It's seen almost every day with Himawari. and it's looking at it in 16 bands across infrared and visible, which infrared is very important for understanding dust absorption. So they went out, got data on what these different spectral bands look like so they could do some real science with them and reprocessed all the data. So it's multi-wavelength. It's looking at 16 bands, like I talked about, visible to infrared. It was launched in 2014. So they had, this happened in 2020. They had a long time curve they could, or light curve they could make over time. Here's just one of the visible channel. You can see kind of what the periodic dimming looks like, and then this giant dip here at the great dimming, and then coming back up. So they were able to make this 4.5 year, 16 band photometry light curve of Betelgeuse between 2017 and 2021. So given that long history and very high regular observations. So
so data was sporadic, or is it not?
I think so. I think so.
That's typically a UDVR kind of data set that they collect.
It might have been the specific band. I think they're looking at 10 micron is what they really needed for the dust features. So I don't know. That's a good question. I didn't read the paper enough detail to tell you. So
There's that many people in AFSO that's actually monitoring Betelgeuse.
Yeah.
There's more interesting stars that they focus on.
Yeah, but
yeah.
people monitor most everything. I haven't looked at it, so
It's a good question. Yeah.
And what about other satellites like TESS? Was that up and running 3 years ago? That could have been repurposed. They do really high quality data.
Yeah, I mean, there was a number of papers on this. So the three that I mentioned, I think there were a few other ones as well. So and there's a lot of references again that you can poke at and see what else is out there.
Graphic work to try to get a handle on the dust or whatever.
Well, they did a lot of that here. And they have some model. They just let me just go to the next chart.
Okay.
It may or may not answer your question. Probably won't. But what they were able to do with that long-term data is put together a spectral energy distribution, which is basically looking at where across the spectrum is the energy being emitted. And with that SED, you can actually fit a number of different models. And again, with that curve over time, they can look at those models over time and see which ones continue to maintain a good fit over time. And they were able to use these light curves, these measurements, to characterize some key parameters to help understand the source of this. So the radius, effective temperature, extinction, and dust optical depth, specifically at 10 microns to, and I have a hanging Chad here. Authors confirmed, so that's supposed to say the hybrid theory. So that one it's a combination of a temperature drop plus some sort of dust emission that obscured the star based on their data. So the key parameters that help these HIMWAR-8 observations distinguish between the models is being able to characterize the dust optical depth out at 10 microns. And you can see kind of that bump in the SED out here where you see the dust features. And I think on this chart, they actually show this over time, these different features. So they were able to confirm, well, here's the dimming. This is just the visible image or brightness. Shows the great dimming. You can see they did confirm one, there's a temperature rise because their models can predict the temperature based on what the model matches. The models match the data best. So you can see this temperature rise, but they also saw this rise in the optical depth, or basically an obscuration from dust, again leading up to and through the great dimming. So the effective temperature, that change in temperature was only able to account for part of the great dimming. This being able to measure the dust features was able to confirm that it really was part of the hybrid model. And they have some follow-up. This is a pretty short, it's a Nature letter, so it's a pretty short discussion, mostly focused on observations. But they did talk about next steps to kind of look at further improving the model, trying to understand the origin of the dust, where it came from, because there's basically two populations. There's a population that can cause this dust very close to the photosphere, and then one a little bit further out, this low lower temperature. Their initial speculation is this population is up a little further out on the surface, but again, they basically didn't draw any strong conclusions there. They said follow-up observations would be good, but the bottom line is this was kind of a surprise. It was really exciting to see in my newsfeed that we're using our weather satellites for astronomy. And this is actually showing, so we showed the light curves, what the imagery actually kind of looked like for feel these over time. Very faint, but you're able to pull a lot of science out of that. And I think this is they always make nice cartoon artist images of what this might look like. So this is kind of the cloud of dust coming over the star. And I think that's all I've got. So I did get a little bit of astronomy in there at the end, mostly life science. Yeah, if anyone wants more details, I got a few copies of the actual paper up here. So, any questions or anything? I probably won't be able to answer a whole lot more on the study than what I said here, but.
You do any astronomy viewing?
It's been a while. So grad school, I had the luxury of being able to go take the big, nice Meade telescopes and go out and take them out in the woods or in the countryside and do observations, but not lately. We have a little tiny Meade ET that's going to take out in the backyard with kids sometimes, but it's so bright. I think the last time I actually looked through a real telescope was probably in Joe's driveway.
Oh, wow.
It's been a while. But I did just join the club, so I'm hoping to come out to one of your Zoom.
You did.
So, yeah.
I heard you mention that, out at the factory there, you grind mirrors, and that you have some surplus, you don't have anything you wanna do.
Yeah, so that was,
3 meter.
yeah, right.
So for 1 meter, I guess, 3, I don't know, you get a 3 meter. I'm so sorry.
So here in town, yeah, so that mirror manufacturing was actually done out between Rochester, and we have another facility in Wilmington, Massachusetts, that does more focused on mirror fabrication. So nothing here in Fort Wayne. We're focusing really on integration and test of a lot of those and design.
You know how fine they grind their mirrors, peak the valley, and
I don't, and if I did, I probably wouldn't be able to tell you, unfortunately. So everything I had to put here is all publicly available and released for public knowledge. So there's some things we just can't talk about. So. Yeah, Cora.
What's your favorite color?
My favorite color, red. 064. Anyone else? 640.
The Taylor guy said was that 4 pixels? Is that the right way to think about it?
Which one? Sorry.
The image of the Betel guys.
Yeah.
So is that 4 pixels?
Um,
That's a good way to think of it. Is that enough to really make a conclusion? You just have to stare at it forever, day after day after day.
yeah, I mean, it's illuminating. Yeah, maybe about 4 pixels on average, pretty thoroughly. So yeah, that's enough to get, with knowing the band pass of all the bands, obviously gonna be brighter in some of the bands than others. This is just the visible. I think, yeah, this is just the 0.64, the 640 nanometers. But yeah, that's enough to, with the spectral response curves that we characterize with all our testing on the ground, they can say how much energy is in each band, and that helps them fit that curve. So basically they are fitting. So these red points are all the channels we look at. This up here is kind of our band pass, our response at each of those channels, normalized to 1. And basically they're taking, once they figure out how much energy is in each of these observations, they're using models to fit this curve and find the best fit as the least residual between the measurements and the models. And then from the models, they're generating these curves that are kind of the parameters of the star and around the dust around it. So
You must be cooling the heck out of these cameras and adjusting for sun side and dark side. All the time.
yeah, so I didn't mention it, but so the visible channels, which are basically the first 6, they're operating at about 170 Kelvin, which is cool, but not that cold. The IR channels, again, you have to be very cold to get good. So you're not picking up the thermal emission of your detectors themselves. They're running at cryogenic temperature 60 K. So that's like minus 350 degrees Fahrenheit. So yeah, very, very cold. And we have to keep them very stable and that cold for 15 years. So that's another very critical challenge for the system. So
You pick up visual, like lightning or sprites.
lightning will be too fast and too faint. There actually is another instrument called the GLM Global Lightning Mapper that has a camera with different parameters, and it's looking for those very fast flashes, and it actually will pick up bolides, so like really fireball meteors that come to the atmosphere, will actually pick those up too, which is pretty interesting.
That'd be the same for sprites then too,
Yeah.
that too fast.
Yeah, so interesting things we pick up, I showed you some of them, fires, the shockwaves in the volcanoes. We'll get really bright glints from solar arrays on the ground, so solar farms will show up when the sun's going over at certain times of the day. But there's, with the different channels, you're looking at really, there's a lot of very good science they can do with those channels. Again, differentiating between clouds and snow on the ground, looking for clear air turbulence. That's a big one too, to route planes around that, because there's some of the water vapor bands we can pick up on basically waves or ripples in the atmosphere that are assigned to turbulence that you wouldn't see because there's no clouds there. It's in the clear air. So we can do things like that. We can track volcanic ash. There's a whole bunch of things we can do with these channels. It's pretty exciting.
You apply filters to different channels out of the picture?
Yeah, there's a series of optics that help filter out the specific bands and meet the band pass requirements that are needed for the weather. Yeah.
So can you track like the flares from like oil installations or gas, and flare up all that natural gas? I'm just wondering if you do that, as anybody in the environmental field ask for access, because they wanted to say, well, you guys say you're only, you're pulling so much natural gas out of the ground, but
Right.
we got all the leaks contained, it's all
Yeah.
great, but like they might be flaring a lot more.
So,
than they're letting-
yeah, so we can see some of those in the thermal bands. We can see some of that, like when they're burning off excess or something like that.
Yeah.
But something that's interesting for the next generation, they're looking at this atmospheric composition instrument, and that's looking for things like trace gases and things like exactly what you're talking about, and trying to
Oh.
characterize that from geo so you get a persistent view. There's some instruments that do that already. They're in LEO, so they don't have that persistent view. They're just getting a snapshot once in a while. But this is something that can be used to track like greenhouse gases and other trace gases in the atmosphere. That's going to be a really interesting instrument for the next gen.
Hmm.
And yeah, you can see the lightning map here too. I mean, that capability, and they're adding another image for ocean color to look for like harmful algal blooms and things like that. That's something,
Yeah, I mean, if you're tracking heat, can't you see like rocket launches all over the place?
you sure can.
Wow, that's cool, man.
Yep.
A shuttle that used to launch out of Florida.
Yeah.
Some of the early news images captured.
Yeah, I had some examples in here, but I cut it because I was worried I was going to go over on time. But yeah, you can see very clearly launches, which is what enables us to support some of our other customers, like the that are looking for missile launches.
That if it's like a classified launch, or how's that work?
That's handle. I mean, they have different. If you watch launches out of the Cape, right, they'll live stream a bunch of them, and some of them will cut off the live stream after certain times, so you can't figure out where they're going.
Right,
So,
but I
yeah.
mean, I was just wondering if your data.
So the weather data, what's nice about the weather data is there's basically every country in the world that has these weather satellites shares the data openly and publicly with every other country, because it's all in everyone's best interest. There's treaties out, I think it's a UN treaty out there to share weather data because everyone wants to improve their forecasts. So like these LEO instruments, like I said, they're global coverage, but only a couple times a day.
Yeah.
So we'll take one of the orbits, the Europeans will take another part of the orbit, and the Japanese will have one up in another orbit, and we'll pool all the data together to inform all of our weather models. So it's a very, good data sharing agreements there.
Is there communication between the geo satellites? Like in the GPS, they'll communicate when they're on certain channels and stuff.
Now they're primarily they're working with the ground system. There's a rebroadcast service where basically the raw data will get sent down, processed on the ground to higher level products that are much smaller in size, and they'll actually bounce that off a relay so our weather satellite actually counts satellite too, so it's bouncing that data off to anyone who has a ground system to get that rebroadcast imagery how they
So
can.
do you like use radars to set a table of where you're at and stuff too?
So for that orbit and velocity data, some of our customers will use ranging data like radars to determine their orbit. We use GPS for it. So yeah.
GPS has to do that.
Yeah.
Okay.
Did we grill you enough?
I think so. Well, thank you very much for letting me come and talk. It's been a pleasure. Yeah.
Much. Appreciate your time.